Okay, so our next speaker is Chiu Yu, and he will talk about geometric models for graded Skew-Gentle algebras.
Yeah, thank the organizer for inviting me to this workshop. In fact, I would very much to come in person. Yeah, because originally, academically, I'm from UK, so I would like to come back every year. But unfortunately, I can only give this talk online. So anyway, I will talk about these geometric models for graded Skew-Gentle algebras and morphisms between arc objects. Yeah, so there's a S here, meaning that we have two geometric models. And one is a classical with tagging, and for morphisms, we have something new. So this is a joint work with Zhang Chao and Zhou Yu. So I will go very quickly on the motivations and this and that, because there are a couple of talks in this workshop on gentle algebras as well as Skew-Gentle algebras, and in particular, for example, Emil's talk yesterday on some band modules. Yeah, so for gentle type of algebras, there are many works, say HKK's work for graded gentle algebras, and also the CARW03 version of gentle algebras. Yeah, and also there are works on derived events by Nakini Potshov and Emil Opper Plamundo Schroer. And also the relation between this CARW03 version and the normal gentle algebras also given in this work. So for gentle algebra, the most easy example and important example is this type A and type A tilde, and everything else is kind of just generalization for these two. So it's natural to study the next case, which is the type D and type D tilde and their generalization. So the classical result in cluster theory for this geometric model is given by Forming, Shapiro, and Thurston. And the tagging I just mentioned is in their work. And also in the work of space of stability condition for associate CARW03 categories of Burban and Smith, they can also deal with punctured case. So now there are a couple of groups of people working on this Skew-Gentle case for various of things. So for example, for the class category, we have this geometric model a couple of years ago. And now for Skew-Gentle, there are many ongoing works. And in this talk, what we aim to do is first just to classify all the objects using just the normal geometric model. That's for the punctures, you just have this tagging, then it's enough to classify objects. But to understand morphisms between them, you need to do some tricks on the puncture, and that's the main new thing in this talk. Yeah, so the plan of the talk is that I will review graded Skew-Gentle algebra and the normal geometric model and classify objects, and then I will introduce another trick to study the morphism between them and show some examples and further works. Yeah, so first of all, in our setting, we want the quiver to have grading. So yeah, this is in some sense because we start from a surface, and then we take a full 4-mark system and we get the quiver. So naturally, it will have arbitrary grading. And so, I mean, if you are starting from a quiver, normally maybe you just start with a normal quiver without grading. Yeah, but we prefer a graded version. So for general algebra, yeah, it appears many times. So I'll just say locally, what could possible happen is that you will have at most 2 in and 2 out, and they pair together, half of them in the relation. So for Skew-Gentle, we first have this Skew-Gentle triple, where that's there are some special vertices which have this loop. And this is still a gentle setting if you take the relation to be square to 0 at this loop. And to get the Skew-Gentle, so this is still gentle. So to get the Skew-Gentle, you replace that relation with this one. So this is not a admissible relation. And this idempotent will split. And basically, what happened is you can delete this and double this versus to have something like that. So this process basically, originally, what you can study is type A stuff. And after you have this loop with this relation, and this is equivalent to split these vertices into 2, so you can get from type A to type D. Yeah, so that's the difference between gentle and Skew-Gentle. Yeah, so you have seen this a couple of times in this workshop. So now we want to have a geometrical model. So this is just modified from the normal gradient mark surface for general algebra. And now the new singularity is that you want to add this puncture. So our setting is that for marked point, we will have the open one and the closed one, where the reason to call them open and closed because in the corresponding quadratic differential on some Riemann surfaces, open marked points are poles for the quadratic differential, and the closed marked point for the zeros. And in this case, sometimes we can allow them to in the interior, but normally we don't, because if you have interior marked point, that will correspond to the, in the general case, correspond to the dimension or the global dimension to be infinite. And we have another set of points in the interior, which is punctures, and it is well known they have this Z2 symmetry, which is this splitting I was mentioned in the last page. So this type of points will be different than the interior marked point. And we have a grading, which you can think as a section of the projectization of the tangent space, or you can think this as an element of the first cohomology class for this projectization of the tangent space. And as usual, that at each point, if you have this tangent go around a circle, it will have this winding number 1. And also, so this is a fixed ending point, and you go around the tangent circle. And another thing you want to fix is that for puncture, and if you fix the direction and you go around the puncture, and that will give you this winding number 1, and that's determined by the singularity property for the puncture. So you have graded curves, and intersections also can be graded by this integer we call the intersection index. So I present this in a non-usual way, and then the normal setting is that you will choose something else. But I would think that for this grading on the surface, it corresponds to this covering, where at each point this is just RP1 at each point. So this direction at each point, and you want to take the lift, Z lift of this. So this Z lift will have this shift 1, which, as you can imagine, correspond to the shift of the triangulate category. So for graded curve, this is just you lift the tangent of the curve to this RTS. So this Z covering of the projectization of the tangent of the surface. So there are exactly Z lift of this tangent. So each curve will give you Z graded version. And for any two of them, if the underlying curve intersect at a point, you can check where do they intersect at which level on the on this covering. So a precise statement is something like that. So basically, one of the lifts of a point so this the lift at that point is R. So the lift of, say, the first direction will divide into intervals, unit intervals, and you just look at which shift of the second lift is living in that interval. So that will tell you the intersection index, which corresponds to the dimension of the degree of the home in the category. So this intersection index can also define at singularities by just looking at what happens in its neighborhood. And so we want to choose a kind of a basis or a generator for this surface. So this is called a full formal arc system, which will divide the surface into this type of polygons. And if we take the closed full formal arc system, then the requirement is that it will contain an open marked point or puncture in its interior. So one should think this as infinite angulation. So in the cluster story, you divide the surface into triangulation. Now you just divide it into any polygon. It doesn't matter how many edges are there. And so from this full formal arc system or this infinite angulation, you can construct a Skew-Gentle algebra which matches the definition before. And as usual, the vertices are just arcs, and arrows are given by angles between those arcs, like things like here. Yeah, so later we will explain that this type of angles will also give morphisms. That's how we understand the corresponding, to calculate the morphisms via this geometric model. Yeah, so the first thing is any graded Skew-Gentle algebra is given by a full formal arc system of some on some gradient marked surface with punctures. Yeah, so this is not hard. And next, we can classify all incomposable objects. So first, the category we want to look at is the perfect derived category, and using open arcs to or open curves, open curves, meaning connecting open marked points, use them to classify things in this category. But duly, you can use closed arcs to classify things in boundary derived category. So the curves we are looking at is we need to eliminate certain type of things, which I draw here. So for example, from Amir's talk yesterday, you see that this type of things will correspond to this type of things. You need to unwind this loop around a puncture. So the same thing here. So we are not allowing this. And we need some local system. If the endpoint of the curve is at a puncture, we will add something like that. And if it's a closed curve, there's something more complicated going on, but this is a little bit technical. And the point is that we have this classification result and saying that any incomposable object in this perfect direct category can be realized as a curve together with some extra information. Yeah, so later I will say that at a puncture, an incomposable module for this is just correspond to ±1. So it's just Z2 choice, which is tagging in the cluster story. And for the first three type of things, we can understand more about them. So classically, the first type is string objects, and here you have a symmetric band object, I think, and the asymmetric band objects, we do not have a good understanding of them. And the proof is basically depend on Burban and Drozd. They developed this machine which tells us that you can glue kind of how to glue polygons together using algebraic language, and we just translate that into our setting plus grading, and then import result from Deng on classification of representation of a bush. And so basically what we do here is just collecting all these things and use the geometric information to say the results. So I have to give the most credit to them for this classification results. Yeah, so next is something new, is that we want to study the morphism between objects of the first three types. So these three types of things, we call them arc objects. So basically, we want they really connect marked point or puncture, and not a simple closed curve on the surface. And in that case, the local system at an endpoint of a puncture, and there are two choices, so correspond to this tagged or untagged, as I mentioned before. So this type of objects, we call them arc objects, and now we want to study the morphisms between them. And the trick we have is that, so we know that for this puncture, there's a Z2 symmetry. And what we want to do is that we want to replace this puncture with a boundary component, which we call a binary. And for this boundary component, we first treat it as a normal boundary. So on it, we will add a closed marked point and an open marked point. And then, so this arc, which is not allowed because in class story, it split into two arcs, one tagged and one not tagged. And now we will split them into these two in the closed full form arc system. And so we need to impose extra condition for this type of boundary component for these binaries, and that's the den square of this boundary component squared to 1. So basically, what I'm saying is that so like if you have this thick blue arc, this will consider the same as this arc. Yeah, so this picture equals to this picture because you just changing this into that. So first, after you add this relation, all the arcs, say from this point, connect to this puncture. After you replace this with boundary components, you should have the z of them because you can just wind this boundary around. But after you add this relation, then there were just 2. So this gives you the Z2 symmetry. And also the other reason we want to do this is that, as mentioned before, in the general case, people know that morphisms are induced by angles at the intersection. So for example, if you have these 2 curves intersect here, so the angle from this arc to this arc, basically these 2 should give you a morphism, and also if they intersect at a boundary component is something like that. And at a puncture, this rule does not apply because there shouldn't be any morphism between these 2 from the class theory, say in the class category. So after we do this modification and with this relation, the point is that for these 2, if you choose these 2 representative, then there's no clockwise angle from this arc to that one at this point. But you have something the other way around. And if you change the representative, you have another way around. But the point is that if you consider clockwise angle from this arc to this arc at this puncture or this binary, you can choose the representative so to kill the possible clockwise angle. Yeah, so now, as I mentioned, that after we have this d square equals to 1 condition, you also have this Z2 symmetry at that boundary, and it's easy to see that a curve connect to a puncture. Originally, you have tagged or untagged. Now you just have 2 choices up to this relation connect to that puncture. So there's a bijection between set of curves here or here. And then to define the intersection number, we just say you choose the representative in your equivalent class to minimize the clockwise angle, those type of intersection, and you can define the intersection number on this surface naturally. And with that, we can prove this type of result that each intersection will give you a basis in the home space between the corresponding objects. Yeah, so this type of result appears in many other works in different settings. So basically, that's what we want to have. And then after you introduce this binary with this relation, this could work. So the proof will, we also need to import some representation results from Guess, where he describes morphisms between representation of bushes. And the other trick, which we use a lot, is just you can cut the long arc into short ones. So yeah, the proof is a little bit technical. Anyway, let's see some examples. So in fact, we want to write down the cone of each morphism, but it turned out it's much more complicated. So at the moment, we can only claim to prove this formula. So the number of intersection equals the dimension of home. But for example, in this case, if you look at these two arcs, they have two intersections from sigma to tau. And if you want to write down the cone, there are four choices. The first choice is if you look at this angle, at this intersection, if you smooth this out, you can have the cone to be the direct sum of these two arcs, the corresponding object correspond to these two arcs. And there are also two more choices. Is the mapping cone can be the direct sum of these two or the tagged version of these two. And another possibility is you smoothing out the intersection here to get this non-admissible arc and unwind this thing to get an admissible one. Yeah, so the point is that it's not easy to describe the cone of the morphism because this dimension and the dimension of the home is 2, but when you choose different combination of bases, there are many choices. But the good thing is using our model that if you just draw things and if you take any two arc and you want to look at how many the dimension of the home, you can just choose a representative to count. Yeah, but to write down the cone of each morphism at each intersection, it's not that easy. Yeah, so yeah, but at least we have a very good picture for presenting say the AI group of type D4. Yeah, so the future works include, for example, we want to understand the AI translation and triangles, Sept condition, and the cone of arbitrary morphisms. So I will only mention this one for fun, is that so after you replace this puncture into this binary, in the previous work with Bruce Lee, we show that in the cluster model with punctures, the AI translation corresponds to tagged rotation. So basically, what does it mean is that if you connect it to a marked point on a boundary, you should just move it to the next one for the AR translation. And if you connect to a puncture, you just change the tagging. And in our model, this should also be true, is that if you move this marked point to the next one, you just would have this one. So this is basically tagged, switching the tag. And if you do this twice, you will get back. So this is also this Z2 symmetry at this binary, which consistent with this tag rotation. Yeah, so anyway, this new binary is our new idea, which allow us to find and calculate the dimension of homes between arc objects correctly. Yeah, and then we can prove that result. So I will finish here.
Thank you very much. Are there any questions? Can't see any in the room. Are there questions in the chat, in the Zoom audience? Just speak up. Actually, I have a question actually. Are you still there?
Yeah.
Oh, your image disappeared because I was speaking there. In your examples, we have seen a lot of morphisms which move the endpoints of the arcs but stay at the same boundary component. Can you also get morphisms where the endpoint moves from one component to another, or from one puncture to another?
Pardon? You mean? Can you repeat?
I mean, if your surface has several components, boundary components, several punctures, if you move an arc from one puncture to another, one endpoint only, or from one boundary component to another.
Yeah, you always say you always move the endpoint at its own boundary component. Yeah, so for example, if there's another boundary component, so you move this endpoint to the next, this to the next. So that's.
But so these are different components of the Außenreitenpulver, then, right? As long as you do that, you stay in the same component of the AR trigger.
Yeah. So if you connect to the same thing, if you move them at the same time, that's the AR translation. And if you have two arcs, you just see if they can use this to get one to the other. Otherwise, then they will in different one.
So my question, I guess, is there are in the module category, there are morphisms which are in the infinite radical, which go from one component to another. I was wondering,
yeah,
if you see them in the surface as
that's
well.
possible. Yeah.
But that's not easy to see, probably, how they look in the surface. It's also not easy to see the module.
Well, yeah, as long as they are arc objects, you just look at if they intersect. Yeah, yeah. The point is that you can count the dimension of home just by looking at if they intersect.
I see. Yes. Thanks. Yes.
I mean, for this, in another situation, like in the module category type A tilde, some of these are described for the annulus, where you move. I mean, you can describe morphisms in the infinite radical with the arcs.
Yeah. So at the moment,
paper that I wrote with Torkildsen.
Pardon. So at the moment, what we're claiming is that we can describe things connecting to a marked point or puncture, but for say this type of closed simple closed curve, that they also correspond to a family of things. We didn't calculate the morphism between this type of things and arc objects or between themselves.
Any other questions? I don't see any, so then let's thank you again.
Thank you.